Okay, so I'd like to welcome everybody to our TSC seminar for the week. And I'd especially like to welcome our three presenters. We have three presenters from INERA today talking about structural analysis of multimode Modelica models. So our presenters today are Albert Benveniste, who was the director of INERA from 1979 to 2014. He is currently emeritus. Albert is IEEE and IFAC fellow. IFAC is the International Federation for Automatic Control, and has been elected to the French National Academy of Engineering. He's made many contributions to signal processing and control, mechanics, embedded system design, and his current interests are in the design of hybrid systems and modelers, particularly in the Modelica language. Benoît Caillaud is also at INERA since 1997. He's currently senior researcher, and his interests include hybrid system modeling and verification, and especially, as we'll see today, scalable analysis algorithms useful for compiling hybrid Modelica models for purposes of simulation and analysis. And Mathias Malandain earned his PhD in 2013 from INSA in Rouen, France, in the area of incompressible fluid flow, also a topic of a lot of interest here at MERL, and is currently an expert engineer in mathematics and software at INERA, and his interests also include analysis of large-scale multimode Modelica models. And so I will now turn it over to the three of you.
Well, thank you, Scott, for the introduction. I would like to thank the organizers of the seminar for the very kind invitation, and we are very pleased to present our current work on structural analysis of multimode Modelica models. So I am Benoît Caillaud, and I will start the presentation with just a brief introduction on the benefits of using differential algebraic equations rather than ordinary differential equations when modeling multiphysics systems. So I guess you all know the Simulink language, and you have here a Simulink model of some physical system. And what you can immediately see is that you don't get the organic architecture of physical device that is modeled here. It is not apparent, and this comes from the fact that in order to model the physical systems using ordinary differential equations, you have to put the system into a state space form. And this completely changes the mathematical structure of your model. And this has a big, and this is a big problem in terms of reusability of models of physical systems. In contrast, when you are using DAEs, so for instance, by using the Modelica language, you can encapsulate the physics of each component of your system into a class. And then your system is just some assembly of a set of instances of class interconnected by connectors. And your model and the architecture of your model exactly reflects the organic architecture of the physical device that is being modeled. And so this tells you that you will have much better reusability of the model, but this comes with a drawback, is that it puts a higher burden on the tools, and in particular, Modelica tools have to perform at compile time a structural analysis of the DAE in order to generate efficient simulation code. So Now let's focus on the multimode aspect of some physical models. So I use the term multimode because it is the term that is being used in the Modelica community, but the terms switched systems or hybrid systems are synonyms. So they mean the same thing. So you naturally find multimode or switched systems when you are modeling some mechanical phenomena. So for instance, Coulomb friction. So multimode models naturally arise when you model dry friction in multi-body mechanical systems. But also when you are modeling thermodynamics, and in particular multi-phase thermodynamics. So here you have some kind of a steam drum, and you have here two phases, steam and a liquid. But the mathematical structure of the model completely changes when one of the two phases disappear. And this is really a difficulty when you want to model such thermodynamics. You also have multi-switched dynamics when you are modeling circuits, such as hydraulic circuits or electrical circuits, because you want to capture instantaneous switchings, either of the electrical circuits or opening or closing valves. When you want to model possible failures of your components in your system, you will use multimode modeling. And more generally, when you are dealing with open systems, so here a smart grid, where consumers and producers can dynamically join or leave the network, you will have to consider switched dynamics. And the difficulty is that although all the facilities have been introduced in the Modelica language several years ago, the handling of multimode Modelica models is far from perfect for state-of-the-art Modelica tools. To understand what is the essence of the difficulty, we'll start with a very, very simple example. It's just 7 lines with 2 equations and 2 variables. So we have one real variable x, one Boolean variable p. The Boolean variable is defined as a function of the real variable, and the dynamics of the real variable is defined by this second equation. So initially, x is initialized to 0, and so the initial value of p is false. I've also forced it here just for a compatibility issue between tools. And so initially p is false, and it is the else part of this equation that defines the dynamics of x. So x increases from 0 to a rate of 1 until it reaches 1, and there the Boolean p changes value and becomes false, and now it's the then part that defines the dynamics. So this model is perfectly fine. It is a fine Modelica model, and this is the expected behavior of the model. Let's see what you obtain with a state-of-the-art Modelica tool. So we have tried several of them, and we obtained the same phenomenon. And actually, you get an exception at time t = 1. So when the Boolean switches from true to from false to true, and you get a division by zero error. Why is that? That's a bit weird. So let's see in detail the root cause of the problem. The problem actually comes from the structural analysis of this model that is performed by Modelica compilers. Essentially, structural analysis algorithms are oblivious to the modes. So they consider that this equation, so the numerical equation is a smooth equation, is treated as a smooth equation. And the structural analysis finds that x prime is the leading variable. It is the unknown that needs to be solved. And this equation is used to compute x prime. But of course, when P is true, this equation cannot be used to compute the value of x prime because it is a singular. It is a singular in x prime when P is true. And so this explains why you get the division by zero error t equal 1. What you should do instead is an exact structural analysis that takes care of the modes and that distinguishes the structure of the model into the two different modes of this system. So when P is false, indeed, the equation can be used to compute the value of x prime. And x prime is the leading variable when P is false. But when P is true, the leading variable is x and not x prime. So we understand the difficulties and the limitations of current Modelica tools that do not implement an exact multimode structural analysis. So we have been working since 2018 on practical structural analysis algorithms for multimode DAE systems. And taking into account a major difficulty of a multimode system is that the number of modes is in general an exponential function of the size of the model. If you have n equations, you will have a number of modes that is in the order of an exponential of the number of equations. And we designed an algorithm that avoids enumerating modes and considers actually the set of modes as a whole. We are currently working on extensions of this algorithm to take care also of the mode changes, because the structural analysis also has to be done at the instance of mode changes. And again, we should avoid enumerating all the possible mode changes. So I will, so Mathias will now give you a gentle introduction to a structural analysis of single mode DA systems, and then we'll move to the multimode case.
I'll do my best. We need to better understand what is structural analysis. And this is something that some people do not really understand. So a simplified way of seeing this is by starting with the very famous example in the literature of a pendulum in a plane. And it is described in the obviously corny way with Cartesian coordinates. So basically, you have three variables, which are x and y, the coordinates of the mass, and lambda, that is that represents the tension in the rod, and the rod is of fixed length. So you have two differential equations for the dynamics and one algebraic equation for basically the constraint that your rod cannot change length. For solving this system, the leading variables in this system are basically the highest differentiations, let's say, of your variables. So here we have the second derivatives of x and y and lambda by itself appearing in the system. And in order to be able to solve this system, you should solve these equations for these variables. And when you compute the Jacobian matrix of the system with respect to these variables, there's an obvious problem, that is the Jacobian is singular. So this system cannot be solved as is. And in fact, what we can guess here is that the problem comes from, in this case, the algebraic equation. We should have leading variables appearing in the third equation, and we do not. So one basic idea that we could have is that by differentiating the last equation twice, we would be able to bring back leading variables into an equation that didn't show any. And so let us differentiate this equation twice, and then the leading variables have not changed. We did not differentiate x to an order greater than 2, same for y, but now the Jacobian matrix is non-singular. So this version, let's say, of the system is amenable to numerical solving, and so time simulation is now possible. And the basic idea of this analysis that is performed on DAE systems is how to differentiate in a clever way some equations so that you will get a system whose Jacobian matrix is non-singular. The question that holds now is how to make this automatic. What algorithms can you find in order to perform this analysis? And how can you make it lightweight? Because you do not wish to actually differentiate the exact equations. And so the solution that was proposed near the end of the 1980s was abstracting away the exact equations and working on a structural version of these equations. And the structural version of equations is only what variables appear in what equations and what are the associated differentiation orders. So in the pendulum example, we could represent this as a matrix that will be filled on the bottom left corner. Or you could show this as a bipartite graph with equation nodes on one side and nodes corresponding to the variables on the other side. These two representations will be perfectly equivalent. And so now let us fill the first row of the matrix. The first row corresponds to the first equation. In the first equation, we have the second derivative of x, the 0th derivative of lambda, and y does not appear. And so the corresponding coefficients will be the maximum orders of differentiation, or it will just be minus infinity, sorry, if the variable does not appear in the equation. The equivalent representation on the graph side is basically adding an edge between an equation and a variable if the variable occurs in the equation, and the weight of this edge will be the maximal differentiation order. And if this is repeated on all equations, we get two equivalent representations that are structural representations of the system. We abstract away the specifics of the equations, and we only keep the information about the occurrence of variables in equations. And this is actually what the term structural refers to in structural analysis. And this is the basis of all the structural analysis algorithms that exist and that have been developed since the 1980s. So we are kind of lifting the curtain here and watching how the Modelica tools in particular will handle the problem of turning a mix of differential and algebraic equations into a system that will be amenable to numerical solving. And several methods exist for finding adequate orders of differentiation for the equations from this structural information. The one we will be focusing on is called the sigma method. It was designed and it was published in 2001 by John Price. And the idea is that basically in two pretty simple steps, the system can be turned into its ODE-like form. So the first step is finding a matching between the equations and the variables. It has to be perfect in the sense that every equation must be matched to a single variable and vice versa. And the weight, that is the sum of the weights of the edges, has to be maximum. And at this stage, you may choose any maximum weight perfect matching if you have several. And then step 2 of the algorithm is applying actually a pretty simple algorithm that will update integer values for variables that we will be calling the CIs and the DJs. There's one CI for each equation and one DJ for each variable. And there's a pretty simple algorithm. The step going from the CIs to updating the DJs is basically maximizing a sum and on each column of the matrix, and going back from the DJs to the CIs is basically performing one subtraction per equation. So then just lather, rinse, and repeat this process until a fixed point is reached. And you get values for the CIs and the DJs that give you the results we expected. That is, the CIs are the differentiation orders that you want from for the equations. And this is exactly the result we guessed by hand, let's say. That is, the third equation should be differentiated twice in order to get a system that is solvable. And the DJs are the orders of the leading variables. So here we have the second derivative of the first and second variables, x and y, and lambda is kept undifferentiated. And this is applied to larger systems in order to get, it's actually how the structural analysis is performed behind the curtain by Modelica tools. At least that's one of the possible methods for this analysis. And now the issue we handle specifically is how to switch to multimode systems, because now we have several changes. The equations themselves are mode dependent. So in this pretty simple example of a circuit in which you want to model a possible failure of a component, you will, at the moment of a mode change, one differential equation will be replaced with an algebraic equation. So the structure of the system changes in the sense that the structural information will change. And so the results of the structural analysis may not be the same in each mode. And this is a source of runtime exceptions with the current state-of-the-art Modelica tools. And the pretty small example that was presented by Benoît at the very beginning of this presentation was a very small example in which we have exactly this issue. And then going further, variable structure systems in which even the number of equations and variables can change is even a further problem for which Modelica currently does not provide a one-size-fits-all solution, in the sense that only fixed-size models are currently accepted in Modelica. And so we wanted to be able to design structural analysis method that would be able to handle efficiently these multimode systems. There are some possibilities that were wiped out pretty quickly for our works, at least. The first one would be just omitting the mode dependencies. But this would amount to exactly the approximate structural analysis that is implemented in state-of-the-art Modelica tools with the kind of results that we already saw. A safe possibility would be enumerating the modes and performing one structural analysis for each mode, but because of the combinatorial explosion of the number of modes, that would be quickly untractable. Another solution was proposed consisting in basically kind of a just-in-time compilation. So the idea would be that at runtime, every time a mode change is detected, the structural analysis in the new mode is performed so that simulation code can be generated on the fly for the new modes. There are a few issues with this approach, or let's say at least a few limitations, one of which is a possibly large computational overhead at runtime. Another limitation is that if a multimode model that somebody wrote is incorrect in not all modes, but in a few modes it's incorrect. Maybe in some mode you have too many equations, or maybe too few equations. This is not something that will be detected at compile time, but something that may be detected at runtime if it so happens that during the simulation the system goes to one of these faulty modes. And we advocate that diagnostics should be provided at compile time, which is why we went to another approach, which is basically representing the mode-dependent structure of the system in an implicit way. I will say a few words about this specific aspect. And then finding a way to perform the structural analysis in an all modes at once fashion. This ought to be performed as efficiently as possible because this is something we would like to perform at compile time in order to be able to provide diagnostics for models that are not well determined in all modes, in order to help the designer tweak their models. So a bit more detail, but I will not delve into too many details on this. But basically, the idea is that when you have a multimode system, you can still extract its structural information. But this time, instead of having simple integers that will tell you the maximum orders of differentiation of variables in equations, these integers will become integer functions of all the possible modes of your system. And so this is something that we wanted to represent efficiently without having to enumerate the modes, sorry. And so we got help from binary decision diagrams, a data structure that's actually more from the verification side. And these binary decision diagrams are a helpful data structure for representing the structure of a multimode DAE system in a compact way and providing efficient ways of computing on them. And this was absolutely needed to alleviate combinatorial explosion, because this also helps us representing an exponential number of modes in a linear number of variables. And then we work on these functions, and we adapted the algorithms that are used for the Sigma method for structural analysis in order to make them work for on functions of the modes, so that in a way the structural analysis is performed on all modes at the same time. And so we published an article that's actually a proceeding for HSCC 20 that explains how the structural information of a multimode DAE is stored and how algorithms are designed on top in order to perform the structural analysis in this all modes at once fashion. This is something pretty lengthy to explain, so please excuse me for skipping this tough part. This has been implemented in a tool called ismDAE that can be tried and experimented with online. So this is the second link provided in this slide, and we will of course provide you with these links. we got, as soon as the structural analysis was implemented, we got pretty encouraging results on multimode models, especially models that were parametric. One of the models we worked with the most, and that illustrates this part, is a pretty simple thermal model of a building with n rooms connected to a single central corridor. And we consider the openings and closings of the doors between the rooms and the corridor as instantaneous switchings. And so we got pretty encouraging results. And then we hugely benefited from a novel compositional algorithm that will, in a very few words, kind of decompose the problem in a clever way into parts that can be then solved in a specific fashion. And we actually gained several orders of magnitude. And so the results we got was that we reach computational times that are, let's say, empirically polynomial in the number of equations, but meanwhile, the number of modes is exponential in the number of equations. And so the tool is currently able to perform the structural analysis of all modes at once for systems that have a few thousand equations for the moment, but we're still working hard on scaling up the algorithms. But even with these few thousand equations, we already handle more than 10 to the 150 modes at the same time, which will be more than intractable if we had to enumerate the mode in any way. The main current limitation of the tool is that there's yet no structural analysis of mode changes that is implemented, but algorithms are on the works in the team, and this is where I let Albert present us our works on the mode changes.
Do you hear me? Yes. Is that okay? Okay. So I will be discussing structural analysis of mode changes. First of all, by not considering the issue of dealing with combinatorial explosion of modes. So I will look into a very simple and basic example so that you can understand the method. So let me investigate again a simple example for illustration. And it is consists of an ideal clutch for which you have the model shown here. For each shaft, you have the autonomous dynamics, which consists of a single equation. And then you have the model of the junction in the middle that says that if gamma is true means that the clutch is engaged. Then the two rotational velocities, omega-1 and omega-2, should be equal. The torques τ1 and τ2 should sum up to 0. And otherwise, if the clutch is released, then the two motions are free. There is no constraint on the relative constraint on the velocity, and the torques are 0. So this is the model that we are going to consider. As a matter of fact, if you try to rewrite this model in state space form, you will see again the complexity that Benoît mentioned at the beginning appearing. So let me focus on, you have the two modes that are shown here. So for the structural analysis of mode changes, we are bothered by the fact that we have to deal with a mix of two different kinds of time. First, continuous time when the clutch is either engaged or released, and then the events that are caused by the changes in the mode from engaged to released and released to engaged when you operate on the clutch. So our first idea was to shift all the problem to discrete time in order to avoid the different nature of time for the two types of phases. So the idea is to discretize the system and not to be bothered by discretization errors. Our idea was to consider what is called an infinitesimal time step, epsilon. And here I will discretize the real line with this infinitesimal time step and consider the shifted, je sais pas si il voit, non, il voit, yes. Okay. And consider the shifted version of x of t, which is defined as x of t plus epsilon. So it's kind of the z transform. And here it's the, you have in the opposite side the z to the -1 by the bullet on the left side. And the derivative is represented by considering the first order explicit Euler scheme for it. So 1 over epsilon times x bullet minus x. And now this is the interpretation that we do in the model of the clutch that is now shown here as at once. Here you have the first shaft, the second shaft, and then the model of the junction with these two modes engaged and released. And what I've done here as a preliminary step, but that was discussed by Mathias, is to perform the index reduction, the structural analysis of the mode change when the clutch is engaged by adding the latent equation obtained by differentiating the constraint that the two velocities should be equal. We could equally well, instead of using first order derivative, differentiating this equation, we could equally well shift it forward once in time, just because the shift and differentiation are related in a mutually invertible way. So structurally, you get exactly the same effect of index reduction. Okay, you should consider that x prime or x bullet are two equivalent representations of the leading variable. So we either work with E prime 3 differentiation or with the shifted variant. And then the rest of the model is there. So we choose the first version in case we are within DAE modes, and this corresponds to the explanation by Mathias before. But at mode change, you will see why. We will be using the alternative version of it, namely the shifting of the constraint to get the latent equation. So this is the model that we get. And what we do to study the mode change is to unfold the model by including in blue the dynamics before the mode change, and in black the dynamics resulting from the mode change. So here we have the release mode where the torques are 0 and there is no constraint on velocity. And here we have the dynamics on the engaged mode in which we have the constraint on velocity, the shifted version of it, to make it structurally regular, and then the constraint on the torques. Okay. So what happens with this model? Remember that because omega prime is interpreted by using the first order Euler scheme, the bullet version of omega prime is given by this formula, namely that the most recent value is omega and the previous value is bullet left omega, which is omega at time t minus epsilon. Okay. So keeping this in mind, we can see that there is a conflicting subsistence involving the three equations with a star Here we have omega 1 and omega 2 involved, no torque. And in the first equation, we have omega 1 that results from expanding this left bullet derivative using the Euler scheme. So omega 1 is present here, omega 1 occurs here, and tau bullet is not a leading variable because we are not considering the leading variable from previous instant, but only the leading variable from the current instant here, the new one. So here we get a conflict with these three equations involving the variable of these two instant systems, which are omega 1, omega 2, omega 1 bullet, omega 2 bullet, tau 1 and tau 2. There are 5 of them. So to handle this conflict, we could reject the model, but this is not. This would not be the good policy to adopt. And the idea is that to resolve the conflict, we have to remove one of the equations, and we give priority to the past. For causality reason, we are not going to change the behavior in the past, but we can let the system wait to satisfy the new constraint that results from the new dynamics. Okay, this is what we are going to do here. So if we do this, then we end up with a final model for restart that is useful to derive how the model should be restarted. And it consists of the new equation in the new mode for the two shafts and only the constraints omega 1 bullet, omega 2 bullet, and tau 1 plus tau 2 equals 0. And these are the 4 equations shown here. And essentially, this is a regular model. You have, you have 4 equations and 4 dependent variables, which are omega 1 and 2 bullet, and tau 1 and tau 2. And this is structurally invertible. So what can we do in the general case? Then let's see what kind of reasoning we should have to apply. We need to find conflicting subsystems. And for this, again, the technique consists in abstracting it as its incidence graph. So it is shown here. You have the assignment, the involvement into a variable into the different equations that are shown in red here. Here you have no variable because tau 1 and tau 2 are considered as states. And here you have the variable shown. And here you just perform what is called the Dulmech-Mendelssohn decomposition of this algebraic system of equation seen as a structural system, which decomposes this system as its underdetermined part, its regular part, and its overdetermined part. And the overdetermined part would consist exactly of the 3 stars listed here that would be found by this Dulmech-Mendelssohn decomposition. So in general, we consider a restricted class of multimode system in which long modes of DAE dynamics alternate with finite cascades of transient mode, because mode change sometimes should operate in more than one instant. For instance, if you have higher order derivatives, you need more steps to do the reset. Now, what do we have to do in a given time slice in red, in handling one mode change? We would unfold the dynamics over this time slice. This gives you an array of equations. We add the latent equation in long mode. This is the sigma method that we heard about. We perform the Dulmech-Mendelssohn decomposition. This eliminates conflicting equation from the long exit mode. If it is still conflicting, then we need to return the conflict to the user. And this is diagnostics that the model is ill-designed. Else, we perform another Dulmage-Mendelssohn decomposition on the remaining subsystem after erasing the conflicting equations. If it is structurally irregular, then we have success and we can evaluate the new value. Else, we return to the user the restarts at which variables are underdetermined. Okay, and we have in our paper, I won't be discussing this here, but we have examples of systems in which this last case here can occur from a practical standpoint. So regarding the implementation of this algorithm in an efficient way, in an all-in-one mode fashion, we already have the multimode sigma method that was presented by Mathias and is already implemented in the tool Malandain. And then what we are currently developing is a multimode Dulmage-Mendelssohn decomposition. So this is already in the tool, but its application to the entire change mode structural analysis is not performed yet. So this is the same approach that we use for the two algorithms. One problem comes with the mode change in multimode system, which is the existence of impulsive behavior. In the case of the ideal clutch, we have this when the physics tells you that there is such a problem, because when you engage the clutch, there is an abrupt changes in the velocity so that the two velocities instantaneously become equal. And as a result, the torques will be infinite for an instant. So they are impulsive. And the question is, what analysis is needed to generate correct simulation code for such impulsive behavior? This is what I'm going to discuss right now. So this is the model I ended up with for the clutch for the release to engaged mode change. And these are the equations that we have to solve for tau 1 and tau 2, omega 1 bullet and omega 2 bullet. And then as a result, we will take the new value for restart, omega plus after mode change, as being omega I bullet. Okay, so this is exactly what we need to do a correct restart. So let's expand the derivative. We end up with this equation. And now the idea is that we are bothered. This is not something that we can implement because tau, the epsilon is an infinitesimal. So infinitesimal is not something that the computers can compute about. So the question is that this is not executable code, and you need to massage it to make it to become something that can be computed by a computer. So what can we do? Epsilon is infinitesimal. So the first stupid idea is that we can replace it by 0, because if it's small, let's neglect it. However, if you do this, you end up with a singular system. So this it makes it structurally singular. Velocities and torques become independent, and this cannot give a solution. The reason is that because we have finite values for the rotation speed, velocities, and epsilon is infinitesimal, at the instant of mode change, where we compute the restart, the tau I is a number that is, so to say, infinitely large, which can be made rigorous in mathematics. And this captures the fact that it corresponds to an impulsive behavior. So there are 3 alternative solutions to this problem, which all give as a final result, essentially, the formula that we have here, which corresponds what could be guessed if you understand a bit about the physics of the system. So we get the correct restart formula without any physical reasoning. So it's really physics agnostic, but still correct. And it reflects the preservation of the angular momentum. So the three techniques are the following. The first one is to eliminate the impulsive variable from the dynamics. So this can be done here because the system, the model, excuse me, has been chosen to be linear for this case. And therefore we can do the elimination and we end up with exactly the equation that we said. Here we have the epsilon appearing in the second member of the equation. And now we can safely set epsilon equal to 0 and we get something that is regular. Okay, so this is the first method. Then an alternative consists in replacing the infinitesimal by something small and computing brute force. As a difficulty, you get something that is poorly conditioned, so which gives you stiffness in the solver that is known to be a source of difficulty. And the other possibility is to rescale the impulsive variable by, if you know the order of magnitude of how tau should be. And if you are able, in this case, a hand reasoning would make it possible to notice that, in fact, if you multiply the infinite tau by delta and do the change of variable replacing it by tau hat, then rescaling would give you a regular system and well conditioned, and that would improve the numerical conditioning of the system. Okay, I think it's becoming a bit too late to go through the details of what can be done in general. Let's just say that in the slides I'm skipping here, I give indication of how to make this systematic for general models. And but this is not implemented yet, and this remains to be implemented in the future. But we have a calculus that again gives a compile time impulse analysis of the system, and that allows you to discover prior to simulation what would be the order of magnitude of the impulsive variable, and to take advantage of this to generate good code. Benoît?
Okay, so thank you, Albert. So it's time to conclude. So we have introduced you to practical and efficient structural analysis algorithms for multimode DAE systems, and that this algorithm, we believe, is of practical relevance in the Modelica community. We have collaborations with some Modelica tool developers about the implementation of our algorithm in their tool. So far, we have scalable structural analysis in all mode at once fashion, only for what Albert called long modes. And it is, Albert has presented a novel structural analysis algorithm for mode changes. And we are working on its implementation in our tool, ISAMDAE. So, yes. And we are also working on a modular version of our multimode structural analysis algorithm. By modular, I mean that you can perform structural analysis on independently on parts of your model, and then combine the partial results in order to obtain a structural analysis of the whole model. And we believe that this will allow us to scale up from a few thousand equations to more to maybe 1 million equations, which is for us the objective. So we still have quite some work to do, and we're still working on our prototype DAE that you can try online. So the link that was in our slides actually is a web service, and you can enter your model, press run, and you will get the result of our tool.
So in terms of structural analysis, it's not simulation.
Only it doesn't do any simulation or things like that yet.
Yes.
Thank you for your attention.
So let's thank our speakers today, virtually or by hand. Maybe what I'll do, I have several questions that are probably more appropriate for a sort of deeper technical discussion in a few minutes, but does anybody in the audience here have any questions they'd like to ask?
Okay, I see one raised hand.
Yeah, just go ahead and ask. Just unmute yourself and ask.
We had for some time a raised hand from Pedro, but okay.
Hey, Scott, I have a question.
Yes.
Yeah, thanks very much for the presentation. So the question that I had was about the use of decision diagrams, right?
Yes.
I mean, we have used decision diagrams, for example, modeling mode changes that happen in discrete optimization problems. And exactly the same reason that you say, right? It gives you a compact representation of an combinatorially explosive solution space. So what exactly is the decision diagram being used for? Is it used, I mean, how is it used for pruning certain mode changes, or how exactly are you using it?
Okay. So we use binary decision diagrams to represent the mode-dependent structure of a model. Indeed, so the bipartite graph that was shown
pretty far back in the slides.
No, we are almost there. We are almost there. So you can imagine that for multimode system, instead of having one such bipartite graph, you have one graph per mode. Okay, so we use binary decision diagrams to represent this huge family of graphs indexed by the modes. And then we use some algorithms on binary decision diagrams to solve the two problems for the structural analysis. So the first problem to solve is to compute a maximal weight transverse for each mode. And for this, basically, what we compute on is both so some maximization of the weight function, that is, and the argmax. So we have an algorithm that does that computes at the same time the max and the argmax for all modes at once. So the result is a function of the modes that gives you the maximal weight and the transverse as a subset of a graph.
And how does the size of the diagram kind of relate to the number of variables and?
Okay, so on the left you have one vertex per equation, and on the right you have one vertex per variable. So this can be fairly large. So these are binary decision diagrams that have several thousand, and then you have one Boolean variable per edge to encode the matching problem. So we handle binary decision diagrams with several thousand of Boolean variables. And this works. So why is it working? Is that actually all these graphs have a very regular structure, but comes from the sparsity of the physical models.
Mm-hmm.
This is really essential.
I see. But so can I take it that the decision diagram actually has only depth 2? Like there's only 2 layers, or are there many more layers in the decision diagram?
No, there's only one layer. It's
Okay.
yes. Yes. So we use since we have a weight function, actually we use a binary encoding of the weight function as an array of binary decision diagrams, and we do our arithmetic on it. It's pretty classic, I would say.
Cool. Okay, thank you. I'll definitely look at your paper then.
Okay. So some of the details are in our papers, and otherwise it is not documented. We have there's a difference between the algorithmic description in our papers and the implementation. There are lots of optimizations that are not in the papers.
Sure. Okay. Thank you.
So I would say at this point, why don't we sort of transition to a discussion among those of us who are perhaps more interested in some of the details. If other people want to drop off, that's perfectly fine. Let's thank you one more time.